All right, good afternoon. So today we're going to talk about section 3.11, related rates. And this is again one section for today. And for the rest of the term, it's just going to be one section. So typically one video that you have to watch, one section of material in the textbook that we're going to cover. And that's going to be the way that it is through the rest of class. So it should be a little less intensive, but still pretty quick. So related rates is mostly just word problems. And you'll see what I mean, because the best way to show you how to do problems like this is just to dive right in with examples. So let's get started. So here's a hypothetical. An oil rig springs a leak and the oil spreads in a roughly circular path around the rig. If the radius of the oil patch increases at a known rate, can we calculate how quickly the area of the patch is changing? And the answer is yes, we can use calculus for this. And you might be saying, this sounds really beyond me, but don't worry, we're going to go ahead and do this example together. So let's start with our example. An oil rig springs a leak in calm seas, and the oil spreads in a circular path around the rig. If the radius of the oil patch increases at a rate of 30 meters per hour, how fast is the area of the patch increasing when the patch has a radius of 100 meters? So how do we set a problem like this up? And the first thing we're going to do, we have two variables that are changing simultaneously, the radius and the area of the circle. But luckily, we've got an equation that relates the two. Area is equal to pi r squared. We know that both the area and the radius are changing as time goes on, so we can rewrite our above expression as area as a function of time is equal to pi times radius as a function of time, quantity squared. And our goal is to find a prime of t, so the change in area over time, given that we know the change in radius over time to be 30 meters per hour. So let's start by differentiating our original function with respect to time. And we have to remember to use the chain rule. So we get a prime of t is equal to 2 pi radius of t times r prime of t. And we're interested in a prime of t when r of t is equal to 100 meters and r prime of t is equal to 30 meters per hour. So we can just go ahead and plug those values in. Now, you might notice that I'm keeping track of my units here. I've got 2 pi times 100 meters times 30 meters per hour. So when I finish, I get 6,000 pi meters squared per hour. So let's go ahead and do a sanity check. Area is measured in meters squared for this problem, and we're interested in the time rate of change of the area. So our final units should be in meters squared per some time unit. And it's convenient that we're using hours. So our time unit is hours. So our final unit should be in meters squared per hour. So we go and we back check the answer that we got, 6,000 pi meters squared per hour. And because our units make sense, we know that our answer is correct. So let's do a general procedure. This is how you're going to go and approach problems like this. And these are just word problems, right? We're just asking you to find the derivative evaluated at a point. That's all. So step one is to make a sketch of your problem. I just stole the image straight out of the textbook, but I had my oil rig in the center and I had a circle that was increasing outwards. Next, we're going to write down equations or just one equation that are relevant to our problem. So in the first one, we just had area equals pi r squared. There was nothing more we needed to write down to relate radius to area of a circle. Then we differentiate the appropriate equations with respect to time. This is a really important step. If you forget that you're differentiating with respect to time, you might forget to use the chain rule, and the chain rule is very, very important. Next, we substitute known values and solve for our desired quantity. It's not always going to be that we're solving for area equals to pi r squared. Sometimes it's going to be a little bit more complicated. There's going to be rearranging. So solving for the desired quantity, make sure we're answering the question we're given. And then finally, sanity check your units. Make sure that your units in the problem match up with what you expect your units to be. So let's do one more example and then we'll be done for the day. So here we've got coffee draining out of a conical filter at a rate of 2.25 inches cubed per minute. If the cone is 5 inches tall and has a radius of 2 inches, how fast is the coffee level dropping when the coffee is 3 inches deep? So there's a couple things in this word problem that might send off some red flags in your head. First of all, we've got coffee draining out of a conical filter at a rate of 2.25 inches cubed per minute. So we've got volume per time. We're decreasing the volume while time elapses. This quantity is going to be negative when we go to start plugging it in. And we can consider this the change in volume over the change in time. So dV dt is equal to negative 2.25 inches cubed per minute. The cone is 5 inches tall and has a radius of 2 inches. Remember, when we start describing cones, we describe the circle of the base as the radius, right? So that's where that 2 inches comes from. And you can see in the diagram we have included that the 2 inches refers to the very top of our cone. And we're interested in how fast the coffee level is dropping when the coffee is 3 inches deep. The level that we're measuring this at is actually the height of our cone. So when the coffee is 3 inches deep, its height equals 3 inches. And we're interested in the change in height as a function of time. So let's see, we've already got a sketch of this, luckily provided by the textbook. Let's see if we can't set up according to the next few steps. We know that the volume of a cone is given by volume equals 1/3 pi r squared times h. And we're interested in the change in height, dh dt, when the height is 3 inches. And we know the change in volume, dv dt, to be negative 2.25 inches cubed per minute. Using similar triangles, we can see that the ratio of the radius to the height of the coffee cone is 2/5 at all time. That is, r divided by h will always equal 2/5, or r is equal to 2/5 times h. So for convenience, we're going to replace our r in our equation with h. So we substitute this relationship for the radius in our original expression. So volume is now equal to 1/3 pi, 2/5 h, quantity squared, times h. And altogether, that's 4 pi over 75 h cubed. And now we can go ahead and differentiate with respect to time. dv dt is equal to 12 pi over 75 times h of t squared times h prime. Now we can substitute in our known values. So we go ahead and do that. And all we're left with is negative 2.25 inches cubed per minute equals 12 pi over 75 times 3 inches squared times the change in height as time changes. And that's exactly what we're looking for. So you can expect in our next step, we solve for dh dt, or we solve for h prime. And it ends up equaling negative 0.497 inches per minute. So let's go ahead and do our sanity check. We're interested in the rate of change of the height with respect to time. So we expect our units to be in inches per minute. And that's exactly what we get. Furthermore, we know that the coffee level is dropping. Material is leaving our coffee cone. So we know that this rate should be negative. We got a negative value and our units match up. We can be pretty confident that this is the correct answer. And that's going to be it for me today.